Hello, good morning, good evening, and good night to all of you. Thank you for joining Optimum AI's session on reinforcement learning with Vidura. Vidura is head of AI in data science with Optimum AI, having 5+ year experience in data science, worked with different companies. Vidura, you can go ahead with your session.
Yeah, thank you. Yeah. So, yeah, we have a Optimum AI. I warmly welcome you all. And yeah, let's me share the presentation. Please let me know that you can see my screen. Oh, okay. I think you can see my screen. Yes. So yeah, reinforcement learning. So today we are going to talk about the important topic, the important subfield of but machine learning with related to AI. So reinforcement learning in a sense like it is unlike the supervised learning, unsupervised learning is a like a very important machine learning technique with the teaching machines to learn from their own experiences, much like how we humans learn from ours. Okay, so it actually tells like how to do like a lot of stuff. Okay, so you will get to know what are the things that we can do by reinforcement learning and so on. Okay, let me with the slides. So here I am, Dhruv Vijayakon. So as like Yahya mentioned, like head of data science AI of the Optimum AI and CEO of Trinet Innovation Private Limited, and as well as work with the Omdena, and I have a bachelor of electrical and software engineering from University of Verona. So I have like 5 year experience with the AI machine learning, with the mentorship experience as well. So yeah, that's kind of a like summary about me. So yeah, let's get into the interesting stuff. So yeah, introduction to reinforcement learning. So, when you hear the word that reinforcement learning, it's like a branch of machine learning. So I actually put the things that I want to express into the presentation. So after the session, you can actually refer those things. So simply it's where kind of there's, let's say, if there's a like a person, if there's a, like an agent, we are calling, let's say let's say we call our person as agent. So a person is there, so he make decision based on where he lives, and where he lives means environment. So the person living in the environment, depending on the environment condition, he just performing some action. Maybe just wake up in the morning, maybe just brushing his teeth, or just walking along the road. That's action. Okay, so based on his action, so there's a kind of a, like cumulative reward. Okay, so reward in a sense, let's say if a person doing something, he will get something in return. That's what get reward means. It can be positive, can be negative. Like if you do good, you will get good results. If you do bad, you get bad. Kind of like similar to our like a human life. Okay, so reinforcement learning is like that, and I think I can explain it in like different example. Think about like how a toddler learns to walk. Okay, so they start by taking a few wobbly steps and maybe sometimes falling, sometimes staying upright. Okay, but each fall teaches them a valuable lesson, something about balance, and each successful step encourages to them to try again and try again. So over time, through a trial and error, they get better. So this process of learning and interaction we are calling, and of course the most important thing, the feedback. Okay, so learning from interaction and feedback we are calling reinforcement learning. So that's a very good example, and I think if you are updated, you know the Google AlphaGo. So Google AlphaGo is defeating the world champion in Go back in 2000, before 2000. So that's another example of reinforcement learning. We will get it to there and shortly. So as I have explained in simple terms that about the toddler, So this is the exact thing that I have put in the presentation. As you can see, it's about agent takes action in environment and receive rewards and learn from this feedback to improve its behavior, like the toddler. So the ultimate goal is to learn a policy that maximizes this cumulative reward. So I have put another example of that robot learning to walk. So it takes like test various movements, so some of which may cause it to fall. It means negative reward, or you can just move forward, the positive reward. Same thing. So yeah. So I have noticed like some of the characteristics of reinforcement learning. So we need to understand this behavior because it helps us to learn the other topics that what we are going to talk about today. Okay. So as we know, the people and animals learn by interacting with our environment. So this differs actually certain from other types of learning. So we call this learning actually active learning, not as a passive learning. Okay, so active learning means like we are like true holders of our own actions. Because of that we are getting rewards. Okay, so the interactions are often sequential. That means whatever the future interaction happening can depend on the earlier ones. Okay, and we are actually goal directed. We are actually reinforcement learning agents, for example, like we humans. Okay, so we can learn without examples of optimal behavior. We don't need to like feel the optimal experience, like the worst case or the best case. We can actually visualize it and we can like learn it. So we optimize some reward signal. For example, if we are having a salary, we go to work every day. That's the reward is the salary. So we are working hard. That's the one other thing. Anyway, so when we are actually learning about this reinforcement learning, there are two things. The first one is the interaction loop. Interaction loop is the thing that what happens in between the agent and the environment. So from the environment, you can see there are observations. So agent observe that as observation, then action will be executed by the agent in order to respond to that observation. So that's called interaction loop. And the reward hypothesis means that actually reinforcement learning totally based on the reward hypothesis. So based on the nature of the reward, so the action will be cumulative and the actions will be optimized. So in order to having a maximizing the cumulative reward, so the action will be proceed and the optimal behavior, like when we are doing something, we try to do the best. That's the simplest term. So yeah, this is another thing like you can see. So in the slide itself says the value based and the policy based and actor and critic. So you can see that there's like a Venn diagram explained about this value function and the policy. Okay, so that means that the reinforcement learning we can actually define as the value based reinforcement learning and the policy based reinforcement learning. So the policy means like there are some policies which govern our actions. Okay, so it says like, okay, this is how you do the things. Okay, that's what policies mean. So the policies actually define our action. And the value base, so the value itself define our action. So the actor critic means the intersection of the both. Okay, so that's the simplest that's the like the explanation, the simplest explanation of this thing. So I will be summarizing all of the things because today itself like I'm going to give the overall aspect of what is reinforcement learning and what are the things that we need to learn. So yeah, so yeah, when we are learning this reinforcement learning, so there are couple of examples. So if we, let's say the example of fly a helicopter, the reward is the air time, the inverse distance that we can travel. If we say like if we want to manage an investment portfolio, so the reward is gains, the gains minus risk. Or control a power station, the reward is efficiency. Or make a robot walk, yeah, distance, speed. Playing video or board games, reward win or maximize score. So yeah, so why we need to learn this? Okay, so the first one is to find solution. Yeah, that's good reason. And the second one is to adapt to the online, deal with unforeseen circumstances. That's that's the reason why this reinforcement learning extend to other type of categories. Okay, adapt to the adaptability. Okay, it's the survivability. So I will explain it in the further slides. So with the reinforcement learning, we had to learn these four things: the RL paradigm. So the state, action, reward, policy. So the state means agent's current decision making situation. Uh, Action means agents move based on the state. Reward means feedback indicating action's effectiveness. Policy means strategic guiding the agent's actions. So, for example, I just like actually lay out the simplest example we can take. Let's say if you are training a dog, so we tell the dog to fetch a ball. So the state is the dog, so dog is the agent, so the dog has to make a decision to take the ball. So the state could be the dog's positive position relative to the ball. Okay, then the action could be running toward the ball, of course. Then the reward could be the receiving a treat if it is successful bring the ball back. The policy the policy a set of behaviors the dog develops to maximize its treats. So you can see the policy is governing how we can get done the action and maximize our reward. So that what the policy is about, and policy is very important. So I will be explaining about the different techniques in the reinforcement learning about this. Okay, so I think you got understand what I have just explained. And of course, the most important another method that I haven't mentioned with this reinforcement learning basic. So we had to talk about the Markov decision process. Okay, so you can just ignore the mathematical concept, but this is the mathematical concept. So for example, like this means like the state, the condition that, let's say, the dog example, the position that we are in. So all we need to know from the history. So like once the state is known, the history may be thrown away. So you can see like if our agent is navigating a maze, for example, so the NDP, the Markov decision process, would model the maze's layout, states, the possible moves, and the chance of hitting a wall or finding the exit. So it will actually predict like how we can go through, how we can execute our action throughout the states. So like if our agent is navigating a maze like a robot following line following robot, so it would model the states, like model maze layout and the possible moves, the actions. So we can then identify the chances, the probabilities of hitting a wall, or like a transition probabilities, and the reward for existing in the maze, because existing in the maze is the goal that the robot should follow. So that what this equation actually tells you, like how the transition probability, like the probability of achieving the goal. That's what the Markov decision process like is about. But I'm not going to further explain about the mathematical concept. Let's just understand the theoretical concept behind this. And yeah, so that's all about introduction to reinforcement learning. So I think you got a good idea about that. So next we are going to talk about the deep policy optimization. Okay, so in the deep policy optimization, as we know, it's a what we call is like one of the approaches optimize the policy through policy gradient methods. Okay, so the catch is that we have to we have to directly parameter what you say we have to directly govern the policy with a neural network and optimize the parameters to maximize the expected cumulative reward. In other words, what we are telling is like we are governing our policy with a neural network. Okay, so this is the method of what we are like method of doing our reinforcement learning. So this is a very important topic. So yeah, this is the infographic of the deep neural network. So deep policy optimization. So as you can see, it actually includes the deep neural network, and you can see the environment, and you can see the action, like that. You can see several components in here. So this is a method that helps us to improve the strategy or the policy that an agent used to make decisions. Okay. So for example, let's say there's like a coach, okay, which coaching a like athlete. Okay. So when he actually trained the athlete, so let's say the more the athlete practices, the better they get. Okay. But the catch is, but to they excel, they need more than just practice. So they needed like a structured training or like a plan their targets and their weaknesses, build on their strengths. So DPO is this structured plan for the learning agents. So in DPO, we use something called policy gradient methods. Okay. So this is policy gradient method. So this policy gradient method means like if we are, let's say, yeah, like I'm a hiker. Okay. So I want to climb a hill. Okay. So I want to climb a hill and we want to reach the top. So we don't know the exact path, but we can see which direction is the uphill. So policy gradient method help me to climb the hill of learning by making small adjustments in the direction where where I can reach as the top hill, like in a sense like where I can going in the direction where maximize my reward. Okay, so I'm a hiker, so I want to reach the top. So, but I don't know the exact path. So what I do is I want to go. I don't even though I don't know the path, but I can see the direction is uphill. So using the policy gradient method, I try to climb the hill by making a small adjustment. So that's what this action feedback and action and this dirt profile and robot position, you can see like different unknown terms, but simple words, this is what happening when we are talking about the DPO. Okay. So yeah. So in other words, what we are saying is maximize what we call the expected return. Okay. So this is the mathematical representation of DPO. So for example, like you can see the policy representation, there are like objective function and the policy representation. So the objective function means like what we have to expect. So what we have to expect is maximize the expected return that I have just mentioned from the start state by adjusting the policy parameters. So the policy is the one which govern us to maximize our reward. Okay. So we actually like fine tuning our policy parameters. So this is the equation, the J theta, E phi theta, the sigma RT. So the discount factor is there and the reward at the step T is there. So this is the mathematical representation. So in here, we are actually controlling how we can fine tune our policy. So then we represent the policy as a probability distribution over action given the state. That means like we actually check what kind of probabilities existed for the agent to execute, for the agent to have the maximum reward. That's what this equation means. Okay. And yeah. So yeah, let me move into the my whiteboard as well. I think you can see my whiteboard. So let me explain it like different example. So yeah. So let's say I'm a chef, okay? So I'm a chef. So I want to make a new dish. Okay, so this is the dish. Okay, yeah, this is the dish. I want to make a dish, the perfect dish. So every time I'm trying to cook, I want to follow a slightly different recipe. Okay, so the different recipe means my policy. So the different recipes means the slightly adjusted policies. Okay, this means policies. Okay, so I want to make a perfect dish. So I'm just trying out like differently, slightly changed like policies. So based on the feedback from people who taste the dish, okay, who taste the dish, like let's say these are the customers. Okay, so here 1, 2, 3. These are the customers. These are the customers. Okay, so customers will taste the dish and tell, okay, this is good and this is bad, or like whatever the thing, okay, this is mild taste, something like that. So whatever the customers telling, they are called rewards. They are called rewards. Okay, they are called rewards. So we have to adjust as a chef. My responsibility based on the customer's feedback, I have to just taste it better, like make it better. Okay, so in the, like, let's say a deep neural network in our recipe, like let's say, okay, the thing that I have just explained is about, okay, you can feel like, okay, this is the reinforcement learning, whatever the customers feel. So based on the customers feedback, I'm changing the dish. Now the tricky part. So in here, we know the DPO, we use a deep neural network. Okay, so we use a deep neural network to represent our recipe. Like it tells you in here, like, even though customers saying, okay, this tastes good or this tastes bad, we have an idea, we should have an idea how to mix the ingredients based on what we have in the kitchen. Okay, so what we have the kitchen means the state. So let's say this is the kitchen. Okay, sorry about that actually. Yeah, this is the kitchen. So the kitchen, we have different amount, like materials to cook our dish, so that's called state. So proportional wise, we have like different vegetables or like fruits. Like you can have like a lot of fruit materials, like food materials. So these food materials, existed food materials, that's called state. So based on the state, you have to make sure how to optimize your like ingredients in proportionally. That part done by the deep neural network. So you can see how to optimize our state. That's what happens in this DPO. So in the DPO, if we are look at our example, so the feedback is kind of like a taste test feedback. Okay, so after each cooking attempt, you ask your customers to taste the dish and rate it. So then you can then update your recipe by slightly adjusting the ingredients. Okay, so in there we can have the like the over the time we can have the perfect dish. So that's about the DPO. Okay, so that's like I'm cooking my pasta, so the pasta might too salty, undercooked, and after several attempts we can adjust the salt and the cooking time based on the feedback. Maybe we invite some friends and they will tell, okay, this is not good, okay, this is great, but too salty, or maybe undercooked, you have to make it more oven. So over the time you end up with a recipe that everyone loves. So this is like how DPO optimize the policy for making dishes. Okay, so yeah, I think you got like a clear idea about that. So the key enhancement in DPO, you will understand this part after I explain that part. So the function approximation, that means like DPO, in the DPO we actually handling the policy and the value function. We are handling the whatever the things are in the kitchen, and whatever the things, how we can mix uh the things, the fruit materials proportionally. That's what it says. Okay, using this DPO. And the trust region optimization means like to prevent large destabilizing update to the policy. That means like whenever the customers are telling, okay, this is test good, this is taste bad, okay, the feedbacks are coming. So that, I mean, taste test algorithm, like the feedbacks are coming, but based on the feedback, it actually prevents the other, like the updates to the policy. The policy is relying on the feedback, and based on that we actually mix the ingredients and we optimize our dish. That's it. And the adaptive learning rate, the next thing is the adaptive learning rate. So it based on the progress of the optimization. So the preventing scenarios, the learning rate is too large or too small. So in a sense, that means like when we are optimizing our meal time to time, it will actually adaptive, like based on whatever the previous customer said, we actually adjust it and then move it. Then the previous mistake that we done, have not mistake repeatedly, and the learning rate based on that like incremented or decremented accordingly. So that's what the key enhancement DPO. And yeah, how DPO actually differs from traditional policy gradient methods. Basically, the stability. So the traditional policy gradient methods like reinforce, each has like a high variance and instability. So when we are training the model, and we have to make sure the policy updates are more stable and reliable. So you can see that DPO, like employees value function baseline. Like for example, if we use the same thing like cooking example, so cook as a chef, I have to like I don't use the DPO, I just have to use the same ingredients at the first instant that and the first state to improve the dish, but it doesn't allow me to improve my dish. Okay, because the policy itself is not trained, and like I didn't got the customer feedbacks. Okay, so in the DPO, I will get the customer feedbacks, and I can actually utilize whatever the things in the kitchen with the DPO, and with the I can like manage the ingredients. But in the traditional method, I cannot do that. So the computational efficiency. So the traditional policy gradient methods, we had to have the carefully tuning of 5 parameters, but in here uh, we cannot like we have the adaptive techniques to have automate this process. And the generalization, same thing. So DPO is better equipped with generalize across different tasks and environments due to deep neural network architecture. That means that like the kitchen itself, the state has like a lot of variation that we can do, so it allow us to do the more generalization rather than the simple one. So yeah, yeah, so I actually explained the same thing like different example, but you can go through this in like another time. And yeah, before going that, let me show you the code. Yeah. Mm, yeah, let me go to the code. So this is the deep policy optimization, how to implement that. So I actually put the same example here. So imagine you are a chef trying to do something. So based on that, I wrote a code. Okay. So the first of all, I define the policy network. So the class policy network, and I define two functions. Like I define state dimension, how the dimension should be of the kitchen, the how the kitchen should be, and what are the ingredients that kitchen should have. These things I have defined in here. Then I have initialized the environment and the policy. So I have defined the optimizer at Adam optimizer, and I will let you like if you ask the question in the Q&A, I will explain about any other like technical questions. And based on that, then I have sample action based on the policy. Then I train the policy using the reinforce algorithm as an example. For example, then in here I like inherit the deep neural network and calculate the cumulative reward and update the policy. So you can see this is the reward. So yeah, these are like 1,000 epoxies are there, epoxy not episodes are there, and the reward you can see it came to stable value. And yeah, we can actually use in the matplotlib, we can actually create like a diagram what happened is. So this is the diagram that we can create. So yeah, so this is the policy network and the environment and the iterative process. This is the reward accumulation. So like that, we can create deep policy optimization implementation using Python. So we just have to play with the torch, and there's a model called Jim. So we can actually play with those things. Yeah, so that's about DPO. Let's jump into the next one, the proximum policy optimization. So the proximum policy optimization is another thing. So let's move into that. So you can see environment is there, agent is there, action is there. So how it differs actually? Yeah, let's move to the whiteboard because it's very efficient and yeah, more practical. Okay, so you can see in here, let's take example like this. Okay, so I'm a basketball coach. Okay, Say I'm a basketball coach. So I'm a basketball coach. So I want to my team to win. So I'm teaching my team a new play. So I want to make sure that any changes make to the play are not too drastic or like are not too complicated. So our players can follow along. Okay. So let's say this is the play field. These are the two ends. Okay. The players are there. Okay. I'm not going to mention, draw the players. So in here, what I'm doing as a coach. So I want to make the players to let's say want to play at their best. So I want the players to help the players to decide what move the players should make based on the current situation on the court. So as our players practices the play, it might make like let's say after that some time it make like me think okay we need to change some position like to more effective like let's say rather than playing that defense rather than playing that strategy we can slightly change the strategy that how we can pass the ball. But if we want to change that we have to make sure these let's say tweaks like tweaks means small adjustment are not too big. If we try to change the like yeah we want to win the game so we want to score as much as possible, but if you are trying to do that by making big changes that means that our players will get confused. So we need to sure as a coach to don't get confused the players and ensure they keep improving without getting overwhelmed by too many changes at once. Okay. So then let's say our team is practicing a particular defensive strategy. So I notice as coach, they are having a trouble with one aspect. So I can adjust their positioning slightly. Then instead of making a huge change, I could confuse them. You make a small, okay. So over the time, this small control adjustment help my team to play better. So that's how PPO works. Okay. So what are the things that I mentioned? Okay, yeah. Let's say this NN. Okay, this NN means what is this? NN is our playbook. So the coach, as a coach, I need the playbook. Okay, so in the playbook, it actually means like it's represented by neural networks. So it helps me to what move in actions. Okay, so the player's actions means it players moves mean the actions. So players should make based on the current situation on the court. Current situation means state. This is state. Okay. So based on the state, as our players are practice the play, we can actually uh, make the small adjustment and make it more effective. This strategy in reinforcement learning called clipped surrogate objective. Okay. Sorry about this. Yeah. Okay. So clipped surrogate objective. So that means the gradual adjustment. Okay. So using the gradual adjustment, we can improve the players and we can optimize our win. So this is called PPO. Okay. So let me go back to here. So we can see the PPO algorithm is there. So this is the environment. Actually, this is a different example, but you can see whenever the action is like feed forward to the environment and the state and reward also affects the agent. So agent tries to like as an agent, I would try to make some small adjustment in order to maximize the reward. Okay. So yeah, I actually explained the motivation behind PPO. So with an good example. So actually in the mathematical sense that policy gradient methods it's powerful, but it's often suffer from instability. Like it has like if we don't do careful tuning of hyperparameters, it leads to the instability and the trust region policy optimization. Like we can use those TRPO to constrain update to the policy, but it makes complex and computationally expensive. That's why we are using PPO. So if we use PPO, what happens is it able us to make small adjustment. So in that sense, we can improve our report. Okay. So in the mathematical sense, it says PPO works iteratively updating the policy, like the coach, way that ensure the new policy is close to the old policy. So you can see the policy is about how to, as a coach, I will define the playbook. Okay, you can, number 13, you can play like this, number 15, number 16, like we have a strategy, like defense strategy. So, but in order to win the game, we are making now small adjustments. So this policy is now changing. So the how did the policy, when we are changing the policy, it like theoretically speaking, it makes some destabilizing update. But to prevent that, we are doing this small adjustment. We actually call that technique called clip surrogate objective. Okay. So this is the equation for clip surrogate objective. So you can see the mathematically it's like complex looking, but it doesn't like this is very simple algorithm. I actually explain in like practical sense. So it actually take the status of the old policy, and it tells the equation to the equation we are telling like we need to do some small refinements. So based on the refinements, okay, new policy should be updated like this. So that E, you can see this small hyperparameter. This is where the threshold which determines, okay, this is how we have to change. Okay. So don't get confused about this mathematical concept, but if you are like a good learner, like if you want to learn more, you can just actually refer this presentation after the webinar. So that's how it is. Okay. So PPO, like with the simplicity and the efficiency, very easy to implement, rather than the TRPO that I mentioned is very complex to handle. And the stability in training, we can use the clip surrogate objective to like the ensure the training remains stable. So whenever I, as a coach, whenever I change the playbook slightly, even with the environment with a high dimensional state, it doesn't get to the instability. And the scalability, it's very highly scalable. Okay. With the continuous action spaces, it's very highly scalable. And yeah, will perform well out of the box. Like it means the robustness. So yeah. And yeah, let me check. Yeah. So let me go to the PPO. So I have also implemented PPO in the simple RL task. So the I actually in here I have used the cardpole environment. So cardpole environment, in a sense, what we are doing is like we are actually using an agent. So the agent, what agent has to do with agent must balance a pole on a moving card by applying force to left or right. So the state space indicates that position and velocity of the card, and as well as the angle and angular velocity of the pole. So these action space actually take the discrete action. Okay, move left or move right. Why I have taken this example? Because this example is the root example which explains the mathematical concept that I have shown in the presentation. We can get the coach example, but it needs more like further additional explanation to explain the mathematical approach. But this is the original concept that when the founders are finding this concept PPO. So the first step is the define the policy network. We can define it by neural network. Then network takes the state as input, and the outputs are the probability distribution or action. So the class policy network. Then define the PPO update text, and define the PPO update using clip surrogate objective that I have explained. In there, we can calculate probability ratio between new and old policies. That means like old playbook, new playbook. And after clipping to ensure stability. So I define the function as PPO update. So in there, I explain like what is the optimizer, what are the states, what are the actions. So we actually take the take the states, action, everything as parameters and feed into our PPO update function. And we actually call the optimizer and make this function to do the clip surrogate objective and calculate the probability ratio. Then after that, the thirdly, we can train the agent. Okay. So in that, when we are training the agent, you can see. So I actually combine all the codes in here. So yeah, in here, I have defined a separate one, compute advantage function. So the compute advantage function, then we can actually start the training loop. So in there, what we are doing is like the cart is going. So we need to make sure, in order to make the balance, whether it is turn left or turn right. So based on that, I have actually defined the trajectory, trajectory, and start the training. So this is the PPO update that I have explained in the upper one, and yeah, for episode in range. So you can see I have trained the reward. Okay, so the reward 12 start with 12, and finally it gets to 14. Okay, using the matplotlib as well, we can kind of like draw something like that. We can generate some kind of graph like this. So the agent learns to balance the poll quickly and effectively. So it actually very useful in the continuous learning task with stable and efficiency. I think you will get good understanding about the PPO as well. So we talked about DPO and PPO. If you have some questions, like we will talk about in the Q&A session, or just put in the chat. Okay, then the next one is the Q learning. So the Q learning, so with the Q learning, it actually find the optimal action selection by selecting the Q value function. But yeah, let me actually explain with an example, as we always do. Wait. Okay. So yeah, this is very simple actually. So Q learning, we have actually like Q learning and deep Q learning. So in the Q learning, like let's say if you are let's say if you are a traveler, okay, you are a traveler in the city, but you don't have any GPS now. Okay, you lost and you don't have any GPS, so you have to make sure like need to survive. So this is the map. Okay, so you actually want to survive from the uh place. So you don't have any GPS. So what you're trying to do is like you need to find the path. So this is less in the city. So you are in the city. So there are road network. Okay, numerous road network are there, intersection are there, and roads, like you name it. Okay, so complex road networks are there. So in here, what we are doing is like we need to find the escape route actually. Okay, so the quickest way out. So this is the out, like a maze. Okay, let's say we are like kind of a rat stuck in the maze. We need to get out. So I have chosen as a person. So this is the exit. We don't know where is the exit. Okay, so with this method, Q learning, we want to try it. We trying to find the quickest way out, and we have no idea where the exit is. So we start exploring. In here, we are using a map. Okay. So in Q learning, we create a simple table which called Q table. Q table. So it tracks the best paths to take from each point in the maze. Let's say when okay, I'm here. No, I'm here. Okay, I'm here. So if we go there, this is a dead end. Okay, this is a dead end. Maybe let's say there's a well here. You can go here, there. This is the exit. Okay. So there's another route. If we go there, there's a jungle, something like that. I don't know. You can go there, and this is another dead end. Okay. So there are like a lot of paths, but let's say, okay, I will go there. The first, go straightly to the well. Then I found out, okay, that's not the exit path. Then I remember that. Okay. So I get an experience. So I execute first action and take from each point in the maze. So from the each action, I will take an experience. Then over the time, every time we hit a dead end, we find a way forward. So in the map, we actually mention that we update our map. Then in the real time, let's say since we don't have any GPS, so when we are going to that dead end, the first few times we might get lost or take long routes, but each time we go, what happens is we remember the streets or that lead to dead ends, and each time we get closer to the destination. So eventually we know the quickest route without even thinking about it. So that's called Q learning. Okay, that's simply called the Q learning. So you can see agent is there, agent performing an action. So the action, even though he's performing action, he will understand what is the state now. Okay, maybe he made to the dead end. Then he will get the reward for that. Okay, the reward is now, okay, you don't have exit right now. Then again perform an action, but when the performing action, the action will be updated in the queue table and help the agent to understand what is happening right now and try to reach the destination. Okay, that's what happened. So that's why it says RT plus 1 every time, every loop it will says RT plus 1. And in here we are like using a concept called Bellman equation. Okay, so the Bellman equation is a concept in reinforcement learning. It describes the relationship between value of a state and value of its successor states. So it's kind of a recursive function. Let's say recursive means like we are actually using the equation itself. Okay, so this is Q and here is Q as well. So this Q is the Q value represent the expected return of taking action, expected return of going the path. R is the immediate reward received after taking action. So after we do go there, we receive a reward. And max QA represent the maximum expected future reward after taking the best possible action from the take A dash from the next state S dash. Dash means like the next state, next action. So you can see it iteratively, recursively it's added, and it recursively tells us like in the map itself, okay, we are close to our destination. Okay, so that this is called the Bellman equation. So this is the mathematical concept. So and this is actually good, what we are calling, you can use the Q learning. This is good example. Like suppose we have 5 rooms in a building connected by doors. Actually I have taken this problem from the internet, from the YouTube video, so I will give the credit to that author as well. So in here I actually see this is a very good fundamental problem to explain the Q learning, but I'm not going to furthermore explain. But in here, what actually do is like we have 5 rooms in a building connecting by doors. So we'll number each room 0 to 4. So outside of the building can be thought of as one of the big room. So the 5 is the destination. So 0, 1, 2, 3, 4, 5 are there. So these doors are the action. Okay. So if we are getting this, so you need to make sure we need first, when you are solving this problem in the Q learning, you have to make sure you have to draw the diagram, like how to perform the action. Okay, so and itself you can mention like how you can what you are saying is drawing the reward. Okay, you can mention drawing the reward. Let me get here. Okay, yeah, we will have time. Yeah, okay, yeah, I will quickly draw it. Okay, so let me take here. Yeah, like this we can draw it. Okay, so you can see there are doors are there. Okay, so key like you can see 0 to 4. So if I'm staying in the 0, I can go to room number 4. Then I can go to room number 3 likewise. So what I do is like Okay, I'm starting by 0 and 4. So I can go to there, 0 to 4. Okay, then I can again from room 4 to I can go to 0. This is both direction. Then from room number 4 I can go to 3. Sorry. From 3, yeah, I can go both direction. Yeah, it's true. 3 to 4. Then after that I can go to 2, room number 2, from 2 to 3. Same way. Then from 3 to 1, same thing. Then room number 5 is the goal state. This is the goal. This is the outside. Okay. So I can 1 to 5 I can go, and 4 to 5 also I can go, and I can go outside as well, like 5 to 5 likewise. Okay. So like this, you can draw the table. You can draw this kind of diagram. Okay. Then let's say if I draw the diagram, uh, what I can do is look at this. I can define a matrix. Okay. So I can define a matrix and action and state. Then you can define as like there are 5 rooms. So I am defining a matrix here. Then based on, let's say 0 to 4, 0 to 4 means I can put the value 0. Then 0 to 5 means that means -1, because there is no way I can go to 0 to 5. That means 0 to 5 -1. So the whatever the parts mentioned here, we can put the values in here as like whatever the values represent here, or otherwise we can put the other values as -1. And the rewards, it should be like the 100, like because we can like let's say in one state to the other, when we are let's say if we are going from one state to the goal directly, that's the reward function. I'm giving a reward as 100. So in here, let's say I can give the reward as 100 in these 3 instances. Otherwise you will get 0. Now based on that, you can fill this state action space. Okay. So based on that, based on this state action space, you can actually try to solve the problem like this using the Bellman equation. So Bellman equation is Q state action, R state action, plus gamma max Q next state all action. Okay, so this is the equation actually. So for example, I will solve one thing. Okay, one operation, then you can calculate the other things. So let's say I am using Q15. Okay, 1 to 5. So if I use 1 to 5, that means R1 to 5. Yeah, R1 to 5. I need to look at this. Okay, R1 to 5 plus, yeah, plus 0.8. I define the discount factor as 0.8 should be given, and max Q1 to 5. Okay, Q1 to 5, Q5 to 4, and Q5 to 5. Okay, so in here what it does is like when we are achieving the goal state means 5. If we are going with the 5, we need to select the maximum Q value of all the paths leading to the 5. So based on that, we are actually out of these three, we are getting what is the maximum value. Okay, so R1 to 5 means 100, 0.8 times 0, because that's the maximum value, and it means 100. Okay, so likewise you can calculate for the other values, and you can draw another what we are calling table. Okay, 0, 1, 2, 3, 4, 5. If you feel like okay, my letters are not clear, please tell me. I will redraw. Okay, I'm just fast forwarding because we don't have much time. This is the matrix. So like that, we can draw. Okay. So yeah, and this is the Q table, and the previous table we draw is R. Okay. So the final one, I think if you are calculating everything, we get like this 80, 100, 64, 64, and 80, 51, 64, 80, 64, 100, 80, 80, 100. Okay, so you can see this is the Q value. Other values are actually 0. That's why I didn't mention about that. So if the agent learned through if the agent learned through the third episode, it will finally reach the convergence value. So like that, we can create the Q table. So using the Q table, we can create the find out. So the what is the quickest path to go. I know that part might some people might get what I have explained, might not. I tried to get some add some like mathematical sense to the understanding. So yeah, that's about the reinforcement learning. Reinforcement learning, Q learning. Then this is the mathematical approach of the Q learning implementation, like coding approach. So as you can see, this is the Q learning. I have defined the environment and I have defined the hyperparameters like running rate, discount factor. In there also, I have defined the problem 0.8. Now we have used 0.9 and exploration rate epsilon naught 0.1 and episode 1000. Then I have implemented the Q learning algorithm. Then you can see like this, I have select random action, select action with max Q value, then the Bell-Mahon equation. Then it will output every time, each and every time. You can see the matrix that I have manually calculated. It will provide. Then using Matplotlib, it will say like this. Okay, the Q value. You can get it like this kind of graph. So yeah, that's about the Q learning. Let's go to the last one, the Q learning with the deep neural network. Okay, so I had denoted like this. So in here, only difference is we actually use a think about the same example. Okay, think about the same example. So we are lost in the town. So now we actually don't have any map like that. Think about the same thing, but now instead of having a like kind of a let's say in at the first time you have like a notepad something like that and you draw okay this part you can go like that. Now you can have kind of like a further advanced tool like that. Okay, so kind of GPS tracking system. Now we have GPS. So if we are coming with the ML part, it means Q learning we are using Q table. Q learning with deep neural network means we are simply using neural network. Okay, we are not using the Q table in here. So that's a difference. Okay, so yeah, and here's the simplest example. So you can see the Q learning state and action Q table Q value. So we actually obtained the Q value earlier. With the deep Q learning, we are using the neural network and we are feeding the state, and we have the Q value action 1, action 2, action n. That means using our, let's say, rather than having a like a notepad or something like a like a map brochure. Now we have like a kind of like smartphone which has like the Google Maps now. Okay, so that's the neural network analogy for neural network in the smartphone. Now we can update the state means like the map. You can just simply see different routes to exit the town. You can see, okay, if I go there, you can go like this. If I go there, you can go like this, like different parts. So the Q value, action 1, action 2, action n. It will allows you to go with the different actions. And so yeah, Q learning, we know the Q values, we can estimate the Q values, and which helps us to get the expected cumulative reward for taking specific action. And Q dash learning, I mean, with the deep neural network, it's not an algorithm but a theoretical construct. That means finding the Q function with the maximum expected reward. We can have like state action pair. I am in the middle of the city. I want to go to the outside of the city. So state action pair, it will tell, okay, go straight and find the, let's say, a memorial statue or something, and you can turn right and you can go there. That's a state action pair. Another state action pair. You can cross the bridge and go there. So the state action pairs are given with the neural network using the smartphone. So likewise, the Q learning focusing on estimate the Q values, approximate Q dash, while Q learning, it refers to the ideal Q values that will result if the agent compute them perfectly. Okay. So in the Q learning, funny thing is we do mistakes. We can find a well and we can come back and we will understand, okay, this path we cannot go there and we can find another route. But Q learning, Q learning with deep neural networks, it's about, okay, we actually know the ideal value, ideal Q values that we can go straight and turn right. We cannot, that's the difference between the Q learning and Q learning with the neural net. Okay. So yeah, this is actually the same thing. And I have mentioned another example here. So yeah, you can actually get this an example as well in the presentation. So this is about drones and how to use the Bellman optimality equation in here. Yeah, so for the last part, so this is the code that I have implemented here. You can see I have initialized the environment and the Q network. So I have again implement the hyperparameters and function to calculation epsilon, and then deep Q learning. So you can see this is the deep Q learning that I have implemented and train the Q network. And this is the what we are calling is diagram of that. So actually that's it from my side. And thank you for actually attending the session, and yeah, I think you got learn a lot about that. Yeah.